And I wanted to start by talking about schemes and sheaves and group schemes. So, so this will be mostly classical algebraic geometry. So A is my base ring. Commutative with a unit. I'm interested in functors from the category of A algebras to categories of sets, and I'm interested in the category of all these functors. And let me briefly recall what it means for such a functor to be a sheaf in various topologies. So I want X to commute with finite products. This has to be functorial. And if I have a faithfully flat morphism, or I can put more conditions, I can ask it to be a finite presentation, or to be atal, or just a bunch of open immersions. Then these morphisms will induce a bijection between this set and the equalizer of what you see after applying X to this diagram, namely so I have two conditions. Okay. And the fundamental fact is that the representable functors, which are called affine schemes, the representable functors are functors of this form, which extends R to the Homs from the set of Homs from B to R for object in category of A algebras. The fundamental fact is that these are sheaves. So this is the easier half of FPQC descent. Okay, so we have the following full subcategories, starting with the affine schemes over A, and FPQC sheaves over A. And because we're putting more conditions on phi, this means that if your functor is an FPQC sheaf, then it's also FPPF sheaf, Étale or Zariski sheaves. And these are all full subcategories of the category of functor on the category of A algebras. Okay? And the point is that this is a simple category. This is simply the opposite category of the category of A algebras. But we can define things like schemes over A. Or formal schemes over A. Which is smaller than here. Okay. So these categories are closed under inductive limits, direct limits, because you can take the direct limits of sheaves. And what are schemes? So these are X such that it's Zariski locally affine schemes, which I don't define today, but I can define what it means for a functor to be Zariski locally affine schemes. And this is not closed under inductive limits. So I'm saying that the schemes are slightly more general kinds of functors than just representable functors. I mean, so it's a generalization of rings, okay? But schemes are not closed under direct limits, but there are many interesting end schemes. Direct limits of schemes. For example, so again, I can say formal schemes are Zariski locally of the form of this form where I is the ideal of B. So this is not an affine scheme. This is a functor which is inductive limit of schemes. Okay. So say if I have A equals ZP, then SPIF of ZP is defined as at these, and so it will send R to a point, a singleton if P is nilpotent in R, and empty set if not, right? If I consider this formal scheme, then again, this lives over SPIF of ZP, so the points are empty if P is not nilpotent. If it is, then the T1 and T1 dot Tn has to go to nilpotent elements of R. And empty if not. Okay. So formal schemes and schemes are the category of these things are, of course, schemes and formal schemes are locally ringed spaces, as we all know, but they're embedded inside the category of functors as full subcategories. The remark is that FBQC and FBPF are similar, but there are set theoretic difficulties because because you don't assume that it's finitely presented, so we prefer FBPF sheaves. Okay. Any questions? So groups, yeah. I don't think so. Barsati-Tate groups are inductive limits of group schemes, but they're not always formal schemes. Barsati-Tate groups. Yeah. So instead of sets, the category of sets, I can consider abelian groups or O modules for ring O. Then I get commutative group schemes. My group schemes will be always commutative. Or I get abelian sheaves. Or more generally, O module schemes or sheaves of O modules. So these are the case O equals Z. So let me write FPPF over A O. This is a category of all FPPF sheaves of O modules, which lives inside the functors, O module functors. So what's good about abelian sheaves is that this is an abelian category. Which is O linear. Okay. The kernels are pre-sheaf kernels, and co-kernels are sheafifications of pre-sheaf co-kernels. If I have an ideal of O, and if I have any O module functor, then I can define the functor of I torsion points like that. I mean, maybe I should write AX equals O. Okay. The number theoretic examples we have in mind are the abelian schemes. So these are group schemes. Sorry, I'm writing curly A for the abelian scheme. A is my base ring, which is proper smooth as a scheme. And all geometric fibers are connected. With dimension G. all these properties of schemes can be defined in terms of functors. These are called Abelian varieties if A is a field, and elliptic curves if G is 1. If you have studied the theory of complex multiplication, you will see something with like this. I have a number field and a ring of integers. Well, I usually say A is an OF algebra, but it's not so important at this point. This is just an Abelian scheme with action of OF. So as functors, I can think of it as functors from the category of A algebras to the OF modules. Okay. So if you have an Abelian variety, Abelian scheme, and if I consider the I torsion points, then this is a functor in OF over I modules. And this turns out to be an affine scheme such that if I call this spec B, then B is an A algebra, which is finite and locally free A module. Of rank n f over q I to g. This is the norm of I. The Abelian varieties are difficult, but their torsion points are nice, finite, affine schemes. Now, I specialize to the case where I is a prime ideal, and take the completion and I define a subgroup scheme of my Abelian scheme. So R goes to the union of all p to the m torsion points. Okay. So I'm just taking the union of all the p to the m torsion points as subfunctors. Okay. So this is, of course, IND group scheme. I mean OP module scheme, because you're just taking the union of these affine finite group schemes. So it's not necessarily a scheme nor a formal scheme, but it's an FBPF sheaf. Okay. Why do we think about these things? I mean, so we're interested in Abelian schemes, but these objects are, well, it's less intuitive because they're not varieties anymore, but it's they're IND varieties, IND of zero-dimensional varieties. So the interest lies in the theorem of Serre and Tate. So if I have a field and an Artinian local ring. This is abbreviation of Artinian. Artinian local ring with residue field K. And if I have an Abelian variety over K, sorry, this is characteristic P. Then, so I have an Abelian variety and then an FBPF sheaf over K of ZP modules. Oops, I meant to go this way, but it should be okay. Then the deformations of my Abelian variety to A is in bijection with the deformations of G these are sets. What do I mean by a deformation? I mean a pair of something over A and an isomorphism of my original A and the mod M reduction of A tilde up to isomorphism. Okay. And this goes from A tilde to the associated FBPF sheaf. So this is, of course, over A. Well, yes. This means that we can study the local structure of p-L-type streamer varieties, which are moduli of Abelian varieties. Using these objects. Because the deformation rings are the local rings of moduli spaces. Any question? Let me just take off my slide.
Maybe this is a naive question. So about this rank formula,
yeah.
when you take I to be just P, then it seems to be a little bit incomparable.
Is it weird? Maybe I made a mistake.
Yeah, maybe some, when you take I just to be P, right, P torsion, then,
Yeah.
then a little bit, the formula seems to be not correct. The P torsion is rank.
Yeah. How do I correct this? So do I have to divide by a degree somewhere, maybe? I'll correct it tomorrow.
Yeah.
Is it just divided by a degree? Yeah, I think this is just, yeah. So this takes us to the Bar-Sauté groups, which was defined yesterday, but I was trying to make it somewhat more precise. So P is a prime. K is a p-adic field. And O will be my ring of integers. P is the maximal ideal, and pi is the uniformizer. Small k will be my residue field. So there I had a number field, but now I'm over a local field because these were all FBPF sheaves of OP modules. So my O will be OP. What do we mean by Bar-Sauté O module? Is an FBPF sheaf is of O modules. Well, I can just say this is a functor. This p torsion, which means if I take the union of all torsions by p to the m, then we get G. P divisible. So I think here I had to assume that it's already an FPPF sheet. Sorry. So we have multiplication by the uniformizer because this was Abelian category of which is O linear. So So maybe I should put this first. This is saying that G for every M, this is an affine over P to the M module scheme. Which is finite locally free over A. So then because of 0 and 1, you'll have G is an N scheme, and it's going to be FPPF sheaf. And then 2 will make sense. Okay. So this is what we saw for Abelian varieties, and I'm just axiomatizing what we saw already. Its height is defined by maybe I should say this is a locally constant function on spec A. So connected. Yesterday we saw the isogenies. This is a morphism in as functors, such that it's an epimorphism, and kernel F is finite locally free. Homodule scheme, right? And sorry for repeating what we saw yesterday, but sorry, and then the height O height of F is H if rank of this kernel, this is again finite locally free, is Q to the H. So O height of G is O height of pi. So quasi-isogeny was just a Hom, an element of Hom tensor Q. Which becomes an isogeny if you multiply by the power of P. So quasi-isogenies are invertible because if F is an isogeny, you can show that exists F prime such that F prime is multiplication by P to the M. So if F is a quasi-isogeny, and then you get an inverse quasi-isogeny. So if A is in characteristic P, so A is any O algebra, but if it factors through the residue field, then I have something called relative qth power Frobenius morphism. So this is the morphism, which is the pullback of the qth power morphism. So this is relative qth power Frobenius. So this is an isogeny. And its O height is called the dimension of G. So more generally, if P is nilpotent in A, so this is R such that P is nilpotent. I have the sheaf of invariant differentials. So what is this? This, if I took the p to the m torsion points of Barsotti-Tate group. This is a finite, locally free group scheme, which means that this is spec B, where B is finite, locally free, A algebra. And because it's a group scheme, so it has an identity section. And the A value point of spec B is just a homomorphism from B to A. So that's E. So what I wrote there is it's just this B module pull back tensoring A to get an A module. So this is this turns out to be independent of M. If my base is P is nilpotent in my base, and this is locally free A module. Independent. So I'll call this omega of G. And Li is the dual of this module. And O this is the same as the the case in the complex geometry or any Abelian varieties, or so these are sheaf of invariant differentials. Its dual is the tangent space. Because G has the action of O, I have the O action on the Lie algebra as well. We say G is compatible if O acting on Lie G. Okay. And this is of rank D. That's what I wanted to say. So this sort of justifies this terminology dimension. Okay. The Messing's theorem is that if GP is radicial over A, what does that mean? This means that spec B and I goes kernel of E. This is nilpotent. Sorry, it's not if, but if and only if. So then, I'm sorry, in this case, we say G is formal. Well, I can write this after. Sorry. Then, as functors or sheaves of sets, it's isomorphic to this FBPF sheaf of sets. So I forget the O module structure, then I get I know that G is isomorphic to this. So these are called formal Lie varieties. So sorry, so this is we say G is formal. Yeah. A, yes, P is nilpotent in A, yes. So I'm almost arriving at the. So let me finish by just saying that sorry. So this yes. Sorry. So all these. So from now on, we're basically assuming that P is nilpotent in A, but especially when A is K bar. this is again done by Segu yesterday. This has this is the one-to-one correspondence between first to take groups up to isogeny. And these are classified by Newton polygons, which is so these are compatible and this is the dimension D. Okay. And the breakpoints are integer, have integral coordinates. Okay. Oops. Maybe I just, yeah. This is my last board, I think. Is that right? What do I need? I mean, when I say isocrystals. Sorry. Is that what you mean? Yeah, sorry. This here I was being sloppy. So. So in this the basic case, so-called basic cases where H and D are co-prime, and I have just one segment, so just a group of self quasi-isogenies of G. So this was central division algebra. Invariant D over H. So tomorrow I'll start with the discussion of Rapport zinc space. For yeah.
Do you really mean that they are co-prime or just they have fingers?
Co-prime and. It's not necessary?
Yeah, it just has fingers.
Okay. Okay. Maybe it doesn't matter, yeah. Maybe it amounts to the same thing after. Well, but then don't you have more? Yeah, so, sorry. So in this case, I wanted to say this is a functor on on O-check algebras. This is the completion of the maximal and ramp-fied extension of O. This has the same maximal ideal as O. This is this is empty if R is not in if P not nilp. In R, I think I needed one more line. So the theorem of Rapport and Zink is that this functor is actually a formal scheme. But I'll start here tomorrow. Sorry for being late.